Okay, so now that we have established our cost function, let's try to understand how we can optimize it. So our cost function is like j is a function of theta 0 and theta 1. These are our two variables for our problem. That is equals to summation of I is equals to 1 to n, where n represents the number of points in the data that we have. For each value, I have yi. I have calculated the predicted value yi prime. I have taken the residual and the square of the residual. So this is our cost function. We want to minimize it. We want to find certain value of theta 0 and theta 1 for which I have the minimum value of this function. Okay, these are called optimization problem. Optimization problem. Okay. So there are many different approaches to optimize something. So here for this kind of scenario, one thing, let's try to understand. Say for example, you start with a certain value of theta 0 and theta 1, a random value. Okay, for a random value you find, so that was the curve. Let's say the points are like this. So these are the points. Now for a random, first you actually select a random value of theta 0 and theta 1. Okay, and you get a curve like this. Say for example the curve was like this. Okay, and you found that the j value that you find, the cost was too high because this is not actually the trend that it is actually representing. So for a particular value, for a first iteration, for the first iteration you get a value. Say for example this was your first iteration, you get j1, but it is not something that is good. So what you have to do, you have to change your theta 0. Say you change it to theta 0. Okay, theta 0 theta 1, let's give it 1. Then again theta 0 and theta 1, let's give it your second iteration. Second iteration you change it and it become like this. Okay, so it actually even worse. Okay, to find a calculation that is increased, the j2 has increased, so that means the way you change the theta was not appropriate. So you update your theta again, make again theta 0 and theta 1. Okay, for the third iteration you calculate, it looks something like this. As you can see now the j value a little bit decreased. Okay, so you have to change your theta again and again and again to find a proper value of j that will give you the minimum error. Now from the scenario you can see there are lots of combination of theta 0 and theta 1. So to do it, okay, one by one iteratively is not a process. It will take a huge amount of time. Okay, it's not a proper process. You have to take some kind of algorithm. You have to undertake some kind of algorithm that can perform this task a much more innovative way. Okay, much more faster. Now this can be done in two ways. One way is called, so before I go there, okay, let's try to understand before I go there. So it is an optimization problem, right? Optimization means, say for example, if I have a curve like this, for example, if this is the curve, so this is the minimum point. This is the minimum point. So for a curve like this, we want to find this minimum point. Okay, that means if I take the gradient of this one, that is the derivative of this one, of the derivative, the minimum of that derivative, that is 0, you know, at this point the derivative becomes 0. So we want to find this point. Let's come here. So if we take the derivative of our original equation, say that was our del j divided by del theta naught with respect to theta naught. So what do we get? There was a square, so it comes first, that is actually 2. Okay, then you have the original one, yi minus theta 0, okay, minus theta 1 xi. There is a summation. There is a summation of this portion for I. Okay. Then again you have to take the derivative of this portion again, and you will see for theta 0 you will get a minus 1. Okay, so the minus will come again. So this is first, then again del j with respect to theta 1, that is the second variable. You have two variables. For that you have to calculate the derivative again. So it will give you something like this, minus 2 summation of yi minus theta 0 minus theta 1 xi. This one will be multiplied by xi, because this one you have to derive again, perform derivation again, will get xi here. Okay, so this is the equation, these two equation you get. Okay, these are the derivatives, right? So the derivative, the curve that actually looks like something like this, it can look like this, it can look like this, any of the curve, any of the shape. You want to find the minima of that curve. Okay, that is the optimization problem. How do you find the minima? You set this point to 0, you set this equation to 0, you set this equation to 0. Okay, because at this point the minima will be 0, the gradient will be 0. So if we come here, curve, the equation will look like now summation of yi minus theta 0 minus theta 1 xi, that is equals to 0. Minus 2 is divided by 0 is equals to 0. Again summation of, you have another yi minus theta 0 minus theta 1 xi, this whole one is multiplied by another xi, so this is also equals to 0. So you have two pair of equation, okay, the gradient of the equation that you have collected. Now from this equation you have to solve for this equation. The question is how we can do that. Now one way to do it is actually using iteration. Okay, that is the iterative method. To understand the iterative method, you can think of it like this way. You have this curve. So say for example the curve is like this. This type of curve is called a convex functions curve. Okay, so at this point, say you have a value of the gradient becomes like this. So what do? You change the theta 0 and theta 1. Say you jump from here to here. Okay, you jump from here to here. Then again you update the theta 0 and theta 1. You come here. Okay, you may actually take some value, it may go here. So you try to decrease again to come here, then again come here. So iteratively you actually try to hone in at this position, because this is your position, this is your desirable position. Okay, this is done, this process is called a stochastic gradient descent. It is called stochastic gradient descent. This is one popular method, okay, to finding this kind of for this scenario, to optimize this kind of function. Stochastic gradient descent is one of the most popular one. There are other methods like this, like for example BFGS, that is another one. The name is come from the authors who actually published this article. So another one is Adam optimizer. So there are many optimization algorithms, okay, to find the minima, global minima or global optima. Okay, now this is one way. There is another way, that is the algebraic way, that is called using normal equation. Okay, and normal equation is something that was shown in your book, normal equation. But again, although normal equation is shown in your book, it will not work always. Okay, when the value of n is very high, normal equation will fail, or it will take a too long time to converge. This is for a smaller one it is okay, but when the n value is high, that means when you have lots of data, this will give you a very good result in a very small amount of time. Okay, but again this is not discussed in your book, so I am not going to do it. I am going to show you the normal equation one that is been shown in your book. So if you come here, so this is the normal equation that you get. The derivation is not given here. So these are the value. Okay, so this is the value of a1, this is the value of a0, a0. These are the values of the line that we are actually trying to make. So if I write it here like this, so a1, let's understand what was a1. A1 is equals to first n, the summation of x I yi. minus summation of xi multiple by summation of yi, okay, divided by n summation of xi square minus summation of xi whole square. This is your a1, and your a0 is equals to y bar, that is the mean value, minus a1 into x bar. Okay, these are the two equations that you have to calculate. So if you look at your lab manual, so it has done iteratively, so you don't need to do it iteratively, we can do it directly. As you can see, you already know this kind of calculation can be done using a matrix. Using matrix manipulation, we can do it. We can do this one, all of this one can be done using matrix manipulation. So we are going to do it in a similar way. Okay. So if you look at the example that is given here, these are the values of x, these are the corresponding values of y. So I have already the value here. So these are the values of x and these are the values of y. And say for example, if I try to plot it, so if I try plot x comma y, what it is going to give. So as you can see, plot by default creates a line. So this is, you can think of it, this is the curve fitting option. Okay, like the interpolation option like this. But we don't want to do it. Rather, we want to find a line that represents the trend. Okay, so what is the trend? We can create a scatter plot. A scatter x comma y. Let's create it. So these are the value, right? So these are 6 different points. We can actually, from the curve, we can get idea that the line should be somewhere in the middle. That actually shows the trend of the data. Okay. So let's try to do it. First I have, okay, let's do it differently. Numerator. So what was the numerator? That was n, that means 7. It is the length of x. Okay, and let's do it 7. The number of elements, I'm just writing it 7 because there are 7 elements. Multiple by, you have to multiply x and y. Okay, if you try here, so for example, x multiplied by y, what you get? You have to perform, okay, sorry, when you use this sign, this is matrix multiplication and this is element wise multiplication. If you remember from your course multiplication or dot multiplication, so this is element wise multiplication. So we want to perform element wise multiplication. So this is the element wise multiplication. Then we want to sum of all the elements. So that means I have what I want, summation of x dot multiplication of y. That is the first term. Then I have minus. Then what do we have? Summation of x, okay, multiple by summation of y, right? The whole thing also goes inside a bracket. So this is your numerator. So what about the denominator? Denominator is equals to n, that is 7, multiple by summation of x square. Summation of x square. X is the vector. You just want to take the square of it. Summation of x square minus a square of, that means summation of x, summation of x whole square. Okay, so this is your denominator. So your a1 becomes is equals to numerator divided by your denominator. If I run this, as you can see, that is 0.8393. Okay, 0.8393 is the slope of your curve, and for a0, that's equals to mean value of your y minus a1 multiplied by mean value of your x. Okay, mean value of your x. So that is 0.0714, and if you check here, 0.0714 and 0.839. So our equation, so our calculation, what we are doing here, it is correct. Okay, so